Bacteriophages, or phages, are viruses that infect and kill bacteria. These microscopic entities are found everywhere from soil and water to the human gut. Phages are incredibly diverse, with countless varieties yet to be discovered. Unlike other viruses, phages specifically target bacteria. They recognize and bind to specific receptors on bacterial cells, ensuring they attack only their intended targets. This specificity minimizes the disruption of beneficial bacteria, unlike broad-spectrum antibiotics. Phages typically consist of a protein coat encasing their genetic material, which can be either DNA or RNA. Tail fibers attached to this coat allow phages to latch onto bacterial prey and inject their genetic material. This process initiates infection, ultimately leading to the bacterium's demise. The life cycle of a bacteriophage is a fascinating example of the interplay between viruses and their bacterial hosts. The process begins with attachment, where the phage uses its tail fibers to bind to specific receptors on the bacterial cell. Once attached, the phage injects its genetic material into the bacterium. This genetic material contains instructions for building more phages. The phage hijacks the bacterium's cellular machinery, forcing it to produce phage components. The bacterium begins to assemble new phage particles. As the infection progresses, the phage produces an enzyme called endolysin. Endolysin weakens the bacterial cell wall, causing the bacterium to burst open, releasing the newly formed phages. These newly released phages can then infect other bacteria, continuing the cycle. Antibiotics have been a cornerstone of modern medicine, effectively treating bacterial infections. However, overuse and misuse have led to a growing crisis: antibiotic resistance. Bacteria have developed mechanisms to survive exposure to antibiotics. This resistance arises when bacteria are repeatedly exposed to antibiotics, killing off susceptible bacteria and leaving behind those with mutations that confer resistance. These resistant bacteria can multiply and spread, passing on their resistance genes. Infections caused by resistant bacteria are more difficult to treat, leading to longer hospital stays and increased risk of death. The World Health Organization identifies antibiotic resistance as a major threat to global health. Without effective antibiotics, even minor infections could prove fatal. The rise of antibiotic resistance underscores the urgent need for alternative strategies to combat bacterial infections. Section 4, Phage Therapy, a beacon of hope. As antibiotic resistance grows, scientists are turning to a promising alternative: phage therapy. This approach uses bacteriophages to treat bacterial infections. Phage therapy has been explored for over a century but is gaining renewed interest. Phages are highly specific in their targets, infecting only a specific strain or species of bacteria. This specificity minimizes the risk of disrupting the patient's microbiome. Phages can evolve alongside bacteria, ensuring phage therapy remains effective even as bacteria evolve. Phages are naturally occurring and abundant in the environment, providing a vast resource for therapeutic development. Phage therapy holds immense promise as a sustainable and effective approach to combating bacterial infections. With its high specificity, evolutionary potential, and natural abundance, phage therapy offers a viable alternative to traditional antibiotics. As research advances, phage therapy could revolutionize the treatment of bacterial infections. Section 5. A success story: phage therapy in action. The potential of phage therapy is demonstrated in real-world cases. One example involves Isabel Carnell Holdaway, a 15-year-old girl from England who contracted a severe bacterial infection after a double lung transplant. The infection, caused by a multi-drug resistant bacterium, spread throughout her body, putting her life at risk. With few treatment options, Isabel's doctors turned to phage therapy. Researchers at the University of Pittsburgh identified 3 phages that showed activity against Isabel's specific strain. The phages were administered intravenously and topically to the infected wounds. Within days, Isabel's condition improved dramatically. After months of phage therapy, Isabel made a full recovery. Isabel's case highlights the efficacy of phage therapy in treating difficult-to-treat infections. Section 6. Challenges and future prospects: phage therapy's journey. Despite its potential, phage therapy faces several challenges. One significant hurdle is the regulatory landscape. As phages are biological entities that can evolve, their approval requires a different approach compared to traditional pharmaceuticals. Regulatory agencies are developing frameworks for evaluating the safety and efficacy of phage therapy. Further research and clinical trials are needed to establish standardized protocols. Public awareness and acceptance of phage therapy remain limited. Educating healthcare professionals and the public about the benefits of phage therapy is crucial. Despite these challenges, the future of phage therapy appears bright. With continued research and regulatory support, phage therapy holds the potential to revolutionize the treatment of bacterial infections.